It's Paul. Welcome to the last Math 23C script. I hope this one will enable you to visualize divergence and curl in a way that's difficult without some computer graphics help. I'm going to have to take some derivatives and evaluate some Jacobian matrices, so I've installed a nice little library named numderiv to permit me to do this. And now I'm going to plot a vector field and its derivative. So here's my vector field. The vector field has two components, the x component and the y component, and I've specified functions of x and y for each of these two components. It's also useful for purposes of the library that I just installed to write this function so that it takes a two-component vector as its argument and returns a two-component vector as its value. This is the same function, just specified differently. I'm setting up for a plot. Something that I haven't been doing earlier in the course that I probably should have is to make the margins as small as possible. I've left on the left-hand side and the top enough space to plot numerical values, but otherwise I'm using all my space, as you can see over on the right. Don't worry about the details of how to plot these arrows unless you try to do it yourself. But what I've done is, at selective points, to plot arrows that represent the vector field. The vector field assigns to every point, there's a point, a vector. Now what we're going to do is look at the derivative of this vector field, and thanks to the library I installed, I just have to call a function Jacobian, and I immediately get the Jacobian of the vector field at x equals 2, y equals 2. Now what we have is a vector field that takes an increment vector called little h and specifies the change in the vector field f if we add that increment to the argument. And what I'm going to use is sequences that run from minus 0.1 to plus 0.1 every 0.02. Now I can plot that field. Don't worry about the details. Just look at this plot. And what's it saying? It's saying as we move away from our anchor point, 2, 2, and we add on a certain increment, here's the change in the field. And what you'll notice if you look at this is if we move away in any direction, we seem to create a change in the vector field that points in the same direction that we moved it. In other words, these arrows are preferentially going out. You can also see the arrows tend to circle around in a counterclockwise sense rather than a clockwise sense. The outness is going to turn into divergence. The counterclockwise-ness is going to turn into curl. So let's figure out how we can calculate these. Specific increment vector, x component 1, y component minus 1. I can take this Jacobian matrix, a 2 by 2 matrix, apply it to that increment vector and take the dot product with the increment vector. And for this specific example, I got 6. But what we really should do is average over increment vectors in all directions. In 2 dimensions, this is easily done. What I'll do is generate a random angle by using a uniform distribution in 0 to 2 pi. And then I will generate a randomly oriented increment vector. I'm going to give it a length of the square root of 2, and then its components will be given by taking the cosine and sine of this random angle. So this is a random increment vector, except that only the direction is random. The length is fixed at the square root of 2. Why did I pick the square root of 2? That means the average value of the square of either component is going to be close to 1. And furthermore, since these vectors are random in direction, if I take the product of the two components, it's as likely to be positive as negative, and the average will be 0. So let me check that. I've just set up numeric vectors to hold the sum of the squares and the sum of the products, and I generate 10,000 of them. And let's look at what we've got. Yes, indeed, the average value of the square of each component is very close to 1. The average value of the product is very close to 0. So now I can take 10,000 random directions. And I will compute what I'm calling outness. The way I calculate outness is I produce this random increment vector. I apply the Jacobian matrix df to it, and then I take the dot product of that with h. If this number is positive, then the vector field is taking me out. If it's negative, it's taking me in. And here's the mean outness. It's about 7. And here's the interesting thing. If I look at that Jacobian matrix, the sum of the entries on the diagonal, the trace of the matrix, is 7. This mean outness is called the divergence of the field. Let's work on curl the same way. You need to remember something about 2 by 2 matrices. If you have to rotate the vector, which is the first column, counterclockwise to get the vector, which is the second column, then the determinant of the matrix is positive. Otherwise, it's negative. So, for a fixed increment vector, the quantity I want to calculate is the determinant of the matrix whose first column is the increment, whose second column is the result of applying the derivative of the vector field to that increment. In this case, it came out 4, but we don't want a single case. We want to do this 10,000 times. So the numeric vector clock is going to hold a number that should be positive if the effect of dx is to rotate the increment vector counterclockwise, negative if the effect is to rotate it clockwise. And as before, I generate a random angle. I use the cosine and sine of that angle to get a random unit vector whose length is equal to the square root of 2. And then I take the determinant of the matrix whose columns are the increment and df acting on that increment. What happened? Well, I took the average of that and got something very close to 3. If I look at the Jacobian matrix, I see, behold, the lower left entry minus the upper right entry is equal to 3. This quantity is sometimes called the curl. Strictly speaking, curl should only be defined in 3 dimensions, but in the 2 by 2 case, you can have a curl which is a number, and it's just the difference between the off-diagonal entries in this matrix. Now let me repeat this analysis using a vector field that's important in physics. The z-axis here is pointing perpendicular to my computer screen, and if I put a long line of positive charge on that axis, I get a vector field which you are about to see. It points out, and the farther away from the line of charge I get, the weaker the electric field becomes. And you can just look at this and say, this looks as though it's pointing out, and it doesn't seem to have any clockwise or counterclockwise tendencies. Let's focus on the derivative right here, where x equals 1 and y equals 1. What happens to this electric field as I move along a small increment vector from that point? Well, the matrix that answers that question is the Jacobian matrix, and having defined my function so that it takes a 2-component vector as its argument and returns a 2-component vector, I can call the library function Jacobian and get it to print out the Jacobian matrix. Here it is. This is a linear vector field. What it does is to take an increment vector as its argument and produce a very good approximation to the change in the electric field as a function of that. I will plot it up, not talking about the details, which have nothing to do with basic mathematics. Here's the plot of the Jacobian matrix, and you can see it's got no in or out tendencies to it. It points in on this side, in on this side, but out there and out there. So the average outness looks like 0. Furthermore, it doesn't seem to have any particular counterclockwise or clockwise tendencies. Here it's sort of running counterclockwise, here it's running clockwise. And those properties result just from the 4 numbers in the Jacobian matrix. So let's go through the same analysis and compute the average outness by using 10,000 random increment vectors. The mean outness is very close to 0. And if you look at the Jacobian matrix, you see that the sum of the diagonal entries is also 0. So this is an electric field whose divergence is 0. This is a characteristic of electric fields in a region of space where there's no electric charge. What about clockwise versus counterclockwise? I do the same calculation. The mean is very close to 0. The difference between the off-diagonal entries is also 0. And as you will learn, if you are taking a physics course or have taken a physics course, the curl of an electric field is always 0. One way of making a field whose curl is 0 is to take the gradient of a function. So let's start with a function, a scalar field. This is a function of x and y. It takes 2 times x times the exponent of the square root of the product of x and y. So this is not a sum or product of functions of x and y. It's a rather complicated beast. Since R can't do computer algebra, I've computed by hand the partial derivative with respect to the first argument x and the partial derivative with respect to the second argument y. I've defined functions f1 and f2 for those 2 partial derivatives, but I've also defined a vector version of this function. This just produces a vector whose 2 components are partial with respect to x and partial with respect to y. Okay, this is a vector field that I can plot. And not only have I plotted it, I have shown the contour lines for my original function f. This is where f has the value 1, 1.5, 2.0, and so on. Why did I do that? Because when I now plot the gradient vector, you can see that the gradient vector is perpendicular to the contour lines. The gradient vector always points in the direction along which the vector field is increasing most rapidly. Now let's focus on the derivative at the point x equals 1, y equals 1. I can use my Jacobian function to get that. And now I can plot the small change in f that results from a small increment. And if I do that, you can see again, this has no overall clockwise or counterclockwise tendencies. It has no curl, and that's a characteristic of the field that you get by taking the gradient of a vector function, because as it's easy to prove, the curl of a gradient is equal to 0. What about the divergence? Well, that's not necessarily 0 on general principles, so let's work it out by computing mean outness. In this case, I get roughly 5.5, and if I look at the Jacobian matrix and take its trace, I get almost precisely the same number. It's almost precisely the same only because this first number was a Monte Carlo simulation. Now let's move to 3 dimensions. What I need to do is again to generate a random increment vector that has an equal probability for pointing in every direction, although its length will be fixed. I'm going to fix the length so that the average value of the square of the x component is 1, same for the y component, same for the z component. In other words, I can do this by making the length of my vector be the square root of 3. This is tricky to do in spherical coordinates, but it's fairly easy to do in cylindrical coordinates. So I will generate z values that are uniformly distributed between -1 and 1. I will generate angles that are equally likely to have any value between 0 and 2 pi. And I will generate 10,000 of these just to check that my expectations are coming out right. And what I discover is, yes, indeed, the square of each component is on the average 1, and the square of the product of 2 components is very close to 0. Now we're in 3 dimensions, and I can't plot this vector field on a flat screen, but I can still compute the average outness. So let's define a vector field now. And because I want to use my nice Jacobian function, I write this as a function that takes the 3 components of a vector and returns a 3-component vector. And since we were using x equals 2, y equals 2 before, let's use x equals 2, y equals 2, z equals 2 as the place where we'll calculate our Jacobian. This works in any number of dimensions. Very nice. There's the Jacobian matrix. Might be useful in doing homework problems sometime. I'm going to do 100,000 values now because the higher the number of coordinates, the more samples you use in order to do a good Monte Carlo approximation. But otherwise, things are much the same. I'm going to generate a random value of z, generate a random value of theta, and then use cylindrical coordinates to generate a vector that has a length of the square root of 3, but otherwise points in a random direction as specified by the components in cylindrical coordinates. And then I'm going to let the Jacobian matrix df act on that increment vector, take the dot product with the increment vector. We've agreed that a positive value means it points out. I compute the mean outness, get 6.5, take the sum of the entries along the diagonal of the matrix, get 6.5. In 3 dimensions also, the divergence is the average outness of the field. I can do the same thing with the curl, but now I need to use a cross product instead of a dot product. So here is a cross product function. It takes 2 vectors, v and w, and computes the first, second, and third components of the cross product. Here is one vector whose squared length is equal to 3, and what I do is to apply the Jacobian matrix to that increment vector and then take the cross product with the increment vector to get another vector. This is a bizarre way of looking at the curl, but it works. The curl is the average value of df acting on h, cross product with h. Let's do this 100,000 times. I do it 100,000 times, and I use the apply function in R to compute the mean of the various components. And when I do that, I get roughly -1.5, +2, and 0. If I look at the Jacobian matrix, and take the differences of the off-diagonal entries, I get -1.5, 2, and 0. This is the formula for the curl in Cartesian coordinates, and what this little demonstration shows is that I can get a very good approximation to that by looking at the expectation of the cross product of H with df acting on H. Now let's finish up with some integration of vector fields along curves. I found a cute library called color ramps that let you generate colors that move gradually from one color to another. And I installed that, and now I'm going to set up a parametrized path. For a parametrized path, I need an interval in parameter space and a parameterization function, which I will call G, and I also need to choose my vector field. So, first my parameterization. The horizontal component is going to be the tangent of my parameter. The vertical component is going to be the secant of my parameter, 1 over cosine of t. So my parameterization function takes a parameter t and produces a vector whose first component is the tangent of t, second component is the secant of t, and I'm going to run from minus pi over 6 to plus pi over 4. Now I need a vector field. Any function of x and y will do. Since I'm staying away from 0, x squared plus x over y is safe, and minus xy plus 1/2 y is a reasonable choice for my second component. I want to plot the parameter space. I'm going to stick that down at minus 0.5. And now I'm going to compute the integral of the vector field along the curve in a manner that's suggested by the formula that's used in most physics textbooks, where you say, take the dot product of force and displacement, integrate it along the curve. I'm going to break my curve up into 40 segments and plot some arrows. Don't worry about the details of the graphics here, just worry about the result. So here is my parameterized path, and you can see that I have broken it up into 40 little pieces. At the tail of each piece, I have plotted the vector field, and if I'm trying to calculate the work done by this vector field on a particle that moves along this path, what I need to do for each little bit is take the dot product of the force and the displacement. Dot product of the force and the displacement. I've computed that. I add up the results, and I get roughly 0.4. But that's not the way one does this in practice. In practice, what we do is to parameterize the curve. So here's my parameter space, and I've got lots of nice little increment vectors, all exactly the same length. And the point of the colors is you can match up the color in parameter space and the color along the path to see which vectors match up. So in parameter space, I have a fixed increment, total length of the interval b minus a divided by the number of increments, and I can sum over those 40 increments. What I do is to calculate the vector field at the parameterized point. So I take a point here, find out where I am on the curve, and substitute that into my two functions f1 and f2. By using the Jacobian, I can get the little vector along the curve, and then what I do is just sum up the dot product of the field vector with the curve vector. And I get a reasonably good value for the integral. I can do a little bit better if I do the evaluation at the midpoint of each interval. That's basically doing a midpoint Riemann sum rather than a left Riemann sum in parameter space. But I can do this much, much better by just evaluating an integral in parameter space. So I say I'll define a function of my parameter t. What I do is take the first component of the vector field multiplied by the partial derivative of the first component of my parameterization function, g1, with respect to t. Grad in this Jacobian package calculates partial derivatives. Then I do the same thing with the second component, add them together, integrate this function from a to b, and I get a result that's remarkably close to what I got when I did my numerical approximation using midpoint Riemann sums. Now to finish off, let me show you what happens if I take a vector field that's the gradient of a function. So here is a function of x and y, minus x cubed plus y cubed plus xy minus 4y plus 5. Any function will do. Using my knowledge of calculus, I define functions for the partial derivative with respect to x and the partial derivative with respect to y. So little f is a scalar field, just a function. f1 and f2 are the x and y components of its gradient vector. Now I can do exactly the same computation as before. All we're interested in is the picture. So here is my curve, same as before, and here is my new vector field. And in order to evaluate the integral of that vector field along this path, what I do is at each little increment of the path, I take the dot product of the force vector and the displacement vector. And when I add that up, I get an approximation to the integral of the field along the path. But that's a silly way to do it. What I should do is just evaluate an integral in parameter space exactly as before. And 2.71, I get a pretty close agreement with my approximation. But in this case, there's a much easier way to get the answer, because if I integrate the gradient of a field along any path, all I get is the change in the value of the function whose gradient I've taken. So if I evaluate my original function, little f, at the endpoint, that's g1 and g2, evaluated on the endpoint b in parameter space, and then I compute the same thing evaluated at my start point in parameter space, and I take the difference. In other words, I take the difference between my original function evaluated at the endpoint and evaluated at the start point. I get exactly the same result as when I integrated the gradient. This is an illustration of what's sometimes called the fundamental theorem of line integrals. Just as a curiosity, I can add the contour lines for my function f to this plot. And when I do that, it took me about an hour to figure out how to do this, so don't worry about the details unless you want to build it into a project. Here are the contour lines for f, and here's what you can see. If you look at any point on the path where we cross a contour line, the gradient vector is always perpendicular to that contour line. Well, this is the longest of all these scripts, but it's the last, and I think I'll send it off to YouTube.